Hello, hello. So just making sure we're on the same page. We're doing the practice review and practice problems for 15, correct? You're muted. Yep. Okay. That's where I thought we were. It's kind of crazy keeping schedule these days, isn't it? Yeah, that doesn't work so well, does it? All right, it's 12 o'clock. I will get started so we can try to get out of here on time. I appreciate those of you that are here and on time. So if I remember what year it is correctly, we are on Module 15, Review and Practice Problems. You'll be getting your review or your Module 15 test this week. I'll be available Tuesday evening. I guess that would have been yesterday. Yeah. Huh. Okay, so we're compressed a little bit. You can get a little flex time. I'll talk to the graders about turning in grades and giving a little extra time for the test since that took a little bit. On Thursday, we'll be starting the last module, which is module 16 on magnetism, I believe. And so we've only got this plus a couple more classes before we are done. So congratulations for sticking through with us. Can everybody hear me okay? Everybody can see everything okay? Audio and video are all good. Just toss something in the chat to let me know, and I'll try to keep an eye on that. All righty. So review questions, and feel free to either jump in on audio because, you know, I'm an extrovert and I like hearing people talk to know you're really there, or chat if you're an introvert is fine. So what is conventional current and why do we use it? Theoretically, you've already got your answers in front of you. Anyone? Bueller?
So, conventional current, it's like an inaccurate representation of like the current that flows in circuits, and ideally it flows from the positive side to the negative side.
Correct. And I just realized the audio on my side is really low. Give me just a second. Let me see if I can get my volume jacked up a little bit here. Oh, no. Mine's up fairly well. So, all right. Maybe your transmitting volume isn't as high. So yes, so conventional current runs from the positive side of the battery to the negative. Conventional current. We kind of do this because historically that's where I think it was Franklin actually started doing a lot of it. That's where they win it from. It goes from this side to that side. However, once we realized what's really going on, we really know that the electrons, the actual charge, is going from the negative to here. So this would be, I don't know, actual current, real current. Sounds like I've got someone shooting or banging something next to me. So real, not roll, real. So while the electrons are actually going this way, conventional, the convention that we have set up is that it goes from the positive to the negative, and we kind of stick with it so that all the circuit diagrams and everything we've done over the past couple hundred years kind of stays intact. We don't have to change everything. So you just have to shift your thinking on that one. So very good. So number 2, what is electric current and what units do we measure it with? Sounding impressive. I wonder if that's coming over the audio there. Anyone? This class is going to take a lot longer if we're going to be waiting here. And I got someone else with me here. Here we go. All right. So question 2, what is electric current? What units do we measure it with it? Yes, preferably someone other than you. 3, 4, 5, 6. Don't make me unmute you. Yes, current is how much charge is running through a circuit every second, and it's measured in amperes. Correct. So if we mark a point in the wire, I'll just do our standard battery symbol here. So current charge is going this way, conventional charge going correct. So if we were to look right here and see how many things pass through every second. So that would be coulombs per second. And coulombs per second we rename to ampere to make it a little easier than saying coulombs per second all the time. So correct. Number 3, explain the concept of resistance in your own words, which means if they're like verbatim out of the answer guide, you're probably not going to get it right. Amp is also correct.
The ability of an object to slow down charge.
Whoops, sorry. Speak up. Couldn't hear you.
The ability of an object to slow down charge.
Yeah, that's one way of looking at it. The actual, book answer is it's the ability of a material to impede the flow of charge when it's subject to a potential difference. So if we put a potential difference across the ends of the wires, yeah, and again, I'm not looking for the exact, I want your words, so that's good. If we put a potential difference, we hook a battery up, apply a potential difference between 2 points on a conductor, the charge is going to flow. A resistor is going to, or something that has resistance is going to impede that flow so it doesn't flow as quickly as it could if it were, say, a superconductor. So there we go. Number 4, how does a switch turn a light bulb on and off? Throwing an easy one out there for you guys. Oops, and we've got an iPhone. Hello, iPhone. All right, so how does a switch turn a light bulb on and off? By removing the path of the electron it's taken in order to power it. Works for me. So again, if we have, I'm just going to draw a resistance because that works for a light bulb. And we just do that. Current's going to flow all the way through. It's going to, light up, give us light. If we put a switch in here, then we can turn the light off by breaking the circuit. We can close the switch, which will have the current flow, and we'll have the light generating. And we've got another late joiner here. All right. So make sure you're on time these last few classes so we don't end up on the end, because we are now on number 5 on the review questions. What is the difference between a series circuit and a parallel circuit? I'm going to leave my circuit there. Difference between a series circuit and a parallel circuit.
In a series circuit, the current must pass it through all of the resistors that are hooked up in a series. And in a parallel circuit, the current has a choice in which the resistor it flows through because the resistors are hooked up in parallel.
Correct. So in a series, it's got to go through all the components in the circuit. So if I had, and resistors are really most of what we talk about here. So this is a series circuit where everything, it goes to the switch, it goes to the resistor 1, or it goes to resistor 2. If, however, we want them to basically go through all the components at a time, essentially, then this is where instead of just going there and having no choice on which way it goes, it actually has branches where it can split and go down this way and down that way as well. And so we actually have, there is current going through each branch. So the phrasing in the book kind of sounds a little weird in that it has a choice. It can go through here or here. It's actually going through both at the same time. So it's going to split and go, and the relative amounts of how much goes through each one depends on, what we've got loaded in different things. Wow, that's really annoying out there. But at least I have internet connection, so I'm not complaining. So where are we at? Number 6. Next page. 6, you observe a string of lights and notice that some are lit while others are burnt out. Is this string of light a series circuit or a parallel circuit? So you may not remember this, but your parents growing up remember their parents complaining every time it was Christmas and we had to pull out the Christmas lights, and you plug them in and the lights don't light up. And you have to go through each individual light bulb to see which one burned out, to see which one you have to replace to make all of them work. It was a real pain. Nowadays, they're just so cheap. You just go buy new ones if you want to. But let's see, we're going to determine like how to buy. Yes, there's a way to determine how the currents divide in parallel resistors, and I can go through some of that if we finish up at the end of the day. So try to remind me before we close out, if you would. String lights, some of them are lit and some are burned out. Trying to guess which question and which answers in the chat we got. Is that the parallel from Jedediah that you think this is parallel if some are lit and some are out? And new messages. This is not auto scrolling for me. Yes. All right. So correct. It is parallel because if, for instance, this bulb burns out, that means there's a break. It's kind of like a fuse or a switch got blown. So there is now no longer any current going through here. But the current can still go through that one and still go through that one. Whereas if this was just a, let's get rid of it, a series, it would break the current right there, just as if we had had a switch, right? And therefore this light would not light up either. So if that helps you remember the series and parallel and which one would burn out, which one wouldn't, that's great. Now 7, 2 identical bulbs are placed in series in a circuit. Okay, so we have a series circuit. Later, we have the same 2 bulbs put in parallel. Compare the brightness of the bulbs when they're in series to their brightness when they're parallel. So which of these circuits is going to put off more light if they're the same bulbs? All the bulbs are the same. Which one's going to produce more light? The series circuit or the parallel circuit?
It should be the parallel one, right? For
correct. And I think we actually did that experiment last week. Yeah, last week makes no sense to me now. A week and a half ago when we had our last class. We did that last class. So yes, the parallel would. We'll get into the calculations on why when we get to the calculations things. That's just a good simple answer. Why do we use fuses, and explain how they work?
To protect something from overvolting or producing too much or having too many amps, and they work by basically melting themselves when they have too much electrons running through them.
Correct. So absolutely correct. A little more detailed answer, I'll always take them and go a little further, is a fuse has a conductor in it that is made of a heat sensitive material. In other words, it's going to melt when it gets too hot. When enough current goes through it, when enough electrons are flowing through it, enough charge is flowing through it, it will heat up and melt. And that is, it's kind of a designed failure point so that the failure point doesn't occur somewhere else that you don't want it to occur, like inside your walls and starting a fire in your house. Number 9, what is the main difference between a fuse and a circuit breaker? The silence is deafening. Circuit breakers bend while fuses break. Circuit breakers are reusable. Yes. So fuses are used one time. When they blow, they're gone. You throw them away, you stick a new one in. Circuit breakers do similar things. They break the circuit to protect it, but they are reusable. They are made of a heat sensitive thing that actually bends and expands. And then, you can put it back in place and use it again. So yes. And the last review question is, what does effective resistance mean? And I don't mean in a governmental perspective. Effective resistance.
I guess I kind of put it in my own words. It was like the resistance going through any type of circuit as a series circuit. So as a parallel circuit, but measured as you would a series circuit.
Okay. Close. I think you're on the right concept. It's basically take all of the resistors, whether they're in series or parallel, and if they could be replaced with a single resistor, what would that resistance of that resistor be? Does that make sense? I think that's where you're going for. But throwing in the extra series in there kind of may confuse the grader, so be careful on that one if it comes up in a test. All right, now we get to, I'll redo all my pictures so I get pretty clean ones. And I'll remove the top when we get to the more complicated parts. So what does the current in the following circuit draw its path? So I'm going to rotate this a little bit because I always like having my batteries over on the side and my resistors over here. But it's the same thing. So this is 120 volts. This is 501 ohms. And we want to know what is the current. So, you know what? We've got few enough people. If y'all want to jump on and kind of talk and walk through, or you just want me to just work them, I'm good with that too. This is a fairly straightforward application of our V equals IR equation. Only we have to rearrange it a little bit, so we'll divide both sides by R. So we're going to get that I equals V over R, which is 120 volts over 50 ohms. Sorry, 501 ohms. And where did I put my calculator? Where's the phone? Where's the phone? Where's the phone? Somebody call my phone. There it is. Got it. 120. Enter. 501. Divide. 0.2395. And this is going to be amps. However, keeping with significant figures, we've got 3, we need to keep 3, so that's going to be 0.240, although the O at the end makes it a little hard, so maybe we want to write that as 2.4 times 10 to the minus 1 ohms. Just so y'all keep the whole thought process there. All right. They answer 0.24 amps, which means they're breaking their own rules here on significant figures. Let's see. Number 2, a circuit is running on a 9-volt battery. Let's see if I can keep the same circuit up here or not. If we do a 9.0 volt battery, if a physicist measures the current to be 0.50 amps, so in this case, our current is 0.50 amps. What is the resistance? So again, same thing. I just gave you the other two different ones, and I'm asking for the third one being different. So here we're going to rearrange to R equals V over I, dividing both sides by I. And so we're going to have 9 volts divided by 0.50 amps, which is going to equal 18. Oops, we don't need anything. 2 significant figures were good. So it's going to be 18 ohms, because that's 9 divided by a half, which is same as 9 times 2. Very good. Awesome. Let's see. Number 3, a motor draws 315 watts of power. It runs on a 120 volt power source. What current does it draw? We can honestly keep the same thing, because a motor in some ways is just a resistance in a circuit. Now it's a resistance that does cool stuff, but we'll just keep the same diagram. Wow, that is really annoying up there. Can't tell if they're banging on something or shooting something. So 120 volts power source. This will draw 315 watts of power. So we don't know what the resistance is there. We do need to know what current it draws. Now we're going to bring in our other equation here, which is power equals current times voltage. So we actually have, it's kind of the same thing. So we want the current, so we're going to rearrange this, dividing both sides by V. We're going to have current is power divided by voltage, which in this case is going to be 315 watts divided by 120 volts, which is going to equal calculator time again. Was it 315 divided by 120? I've got 2.625. And that's going to be amps. So getting that into significant figures, we've got 3, so we're going to keep 3. So we're going to say that's 2.63 amps is our final answer. Book's final answer is 2.6 amps. So I would say, again, they did not do the significant figures the way they should have, because we've got 3, we want to keep 3. That would be a 2.63, right? So let's see. Number 4, a 15 ohm resistor draws 1.2 amps of current. How much power does it use? Great, we can keep the same diagram. Gotta love it. So now we have a 15, resistance is 15 ohms. Current is 1.2 amps. How much power does it draw? Nice, I can draw that over by the resistor, huh? We've been keeping that over there. Well, we don't know what the voltage is to get power. We need current voltage. But we can figure some things out here. Oh, let's combine these. If we remember the other form of this, if we just take V and plug it in here, we get I times R. So that's also equal to I squared R. Well, we have I, we have R, so we can just do this. You can either pull that equation out or go ahead and say this, and kind of derive it in the problem just to make sure that the grader gets it, depending on what the book decides to do. Actually, it does look like the book is using this equation directly, so you should be good, which is going power equals I squared R, which means we just straight plug it in. P equals 1.2 amps squared times 15 ohms. Handy dandy calculator. That's going to be 1.44 times 15. 1.44 enter 15 times. I'm getting 21.6 watts. We've got 2, so we need to keep that significant figure. I've got 22 watts. The book gets 22 watts. Yay, they got it right. Always useful. And we are done with the first page of problems. Boy, we are zipping through this. We're not even 30 minutes in. We'll have plenty of time to do stuff. All right, I haven't even been paying attention to the chat. Holy moly. Can y'all hear that, like, gunfire banging, whatever that noise is? Yeah. That's like a little scary. All right, where's my eraser, guys? There we go. Let's see if we can use this again. No, we can't. They've got a new diagram for us. All right. So determine the effective resistance of the following circuit. So we've got our battery. And this is a parallel one. I'm going to draw it way over so I've got plenty of room to write. This is 151 ohms. This is 215 ohms, and it is parallel circuit. So, hey, at least maybe they're having fun over there shooting, right? See, if this was a public school, we'd have to go into lockdown, but you know, we homeschool, so we don't care if people are shooting guns around, right? Okay, so for the effective resistance in a parallel circuit, and it's also Texas, absolutely. So to do that one, remember the effective resistance, EFF, is equal to 1 over R1 plus 1 over R2 plus ... 1 over, 1 over, 1 over, 1 over, right? So to do this one, we're going to say this is 1 over 151 ohms plus 1 over 215 ohms is 1 over the effective resistance. So let me get those two things done and added together. 151, where's my inverse? 1 over, where is 215? Over, add those two together. So I've got 1 over the effective resistance is equal to roughly, just as a, I'm going to kind of go approximately 0.013, 0.113. Actually, it's exactly that. So then we do a 1 over that. And I'm getting that the effective resistance in here is going to be 88.7022. So 88.7, and that would be ohms. What did the book get? What question are we on? We're on number 5. So many pieces of data holding our hands. 5, effective resistance 88.73 is not what I got. How did they get? I mean, I got it's close, but how did they round that? Because I'm getting 88.7 even. Weird. All right. Anyway, and again, they put 4 significant figures in their answer. They only have 3 in the problems. So yeah, you know, go figure. One reason you don't want to copy the answer straight out of the book if you have access to that. The next problem, we're in series. So I'm going to get rid of this branch and we're going to put a resistor right here. 215, the same 2 resistors. So that one's 215, this one's 151. What is the effective resistance in a series circuit? Well, in that case, it's just R1 plus R2 plus R3 plus R4 plus R5, whatever. So you just add them all up. So in this case, 151 plus 215 is going to be 366 ohms. That's a horrible omega. I am not the omega man. All right, cool. Nice and simple. Now, let's get slightly more complex now that we know how to determine what effective resistances are for circuits. I'll redraw this a little bit bigger and a little bit better because we've got some extra stuff added in, like a 3rd resistor. So I'm going to rotate this as I want to do. Resistor, resistor. Okay, the first resistor is, this is 9-volt battery. So we've got a 9.0 volt battery that is going through a 12.0 ohm resistor, a 9.0 ohm resistor, and a 20 ohm resistor. What is the power drawn on that? Now, whoops, did I have somebody join? Nope, join, drop something. Done. All right, so we're looking for power, which means if we have current and voltage, we can do it. Or if we have the current squared and the resistance, we can do it. We don't have current and we don't have the effective resistance yet. We can get the effective resistance, we still have to figure out the current. So we're gonna have to kind of use all of this to make this happen, all right? Or we can do some algebra first. I'm gonna do it the way the book didn't do it because I think y'all can see the easy way of find the effective resistance, okay, add them all up because it's in series. Divide or take the voltage divided by the resistance to get the current, take the current, square it, and multiply it by that resistance, and you can get that. I'm going to do like a full algebra way through because it's really not that hard, so we get it. So we want the power, right? Power is I squared R. Okay, that's awesome. what is I? I, according to our Ohm's law here, is V over R, right? So that we don't ever have to calculate the current, I'm going to take that I and plug it into here, all right? So we're going to have that power is going to equal V squared over R squared, so that's the I squared, times R. Oops, that R is going to cancel that R, so it's going to be V squared over, in this case, the effective resistance. All right? Everybody kind of follow what I did there? You may not have seen that going in to start with, but this is a lot less math on the calculator, which is much slower for me. All right, so we've got the voltage, we need the effective resistance. The effective resistance is, let's do it over here. Our effective, we're just going to add them up. So it's going to be 12 ohms plus 9 ohms plus 20 ohms. And I got to stretch for that one. So 12, 9, that's 21, so that's 41. Right? And we're keeping, I don't know if we're doing 3 or 2, whatever. I'm going to say we're keeping out to 1 decimal point. So let's call that 41.0 ohms. All right. So now we got that. We got the voltage. So now we're going to go 9.0 volts squared over 41 ohms. That's going to be 81 over 41. So it's going to be about a half of a watt. 81 enter 41 divide 1.9756. 1.9756, and that's power, so that's watts. Let's do that at 3. So we're going to have 1.98 watts. Let's see what the book got. Did we come close? What problem was this? This was number 7. So they got 2.0 watts. So they were keeping, I guess if you round it to 2, that would go up. So yeah, okay. So if we keep that at 2 significant figures, that would round up to 2.0 watts. So yeah, so good. Awesome. 3. What's 3? Oh, 3 sig figs. Yeah, got it. I was like, no, it's 2, not 3. I'm good. All right. See, now in the future, people watching the video are going to have to see like the chat and the video to try to figure out what I'm talking about here, right? All right. What number are we on? We are on 8, I believe. Yes, 8. Determine the power drawn by the following circuits. So this, I believe, is going to be the same 9, 19, and 15. No, they've got different resistors. Of course they do. If I were designing it, I'd keep the same resistor number so you can see how it does differently. But yeah, we'll just get rid of the whole thing. So we have our power source. We have 1, 2, 3. This is 120 volts. I'm having trouble reading these little fine prints here. That's 9, 19, and 15. Ohms, ohms, ohms. I think that's right. Whoop. Ohm slide. We're good. All right. Yep, 9, 19, 15. Cool. Just check to make sure they're good. Oops. All right. So first, we're going to do the same thing, right? Because we need to figure the power drawn. We're going to do the effective resistance, which in this case, 1 over the effective resistance is going to equal 1 over 9.0 ohms plus 1 over 19.0 ohms plus 1 over 15.0 ohms, which is going to equal calculator time. Holy moly. They're either eating through a lot of ammo or they're banging on something. I can't quite tell what. 19, 1 over, plus 15, 1 over, plus. That all is going to be 0.2304, 0.2304. We do a 1 over that, and we're going to get an effective resistance of 4.34. All right. Oh yeah, we're going to do the same thing we did before, which I've now lost. So we put that back in there. We're going to have power is going to equal V squared over R. Is that right? V squared over R squared multiplied by R. Yes, V squared over R. So we've got voltage, we've got effective resistance. So now we have power is going to equal 120 volts squared over 4.34 ohms. I look like I'm writing in kindergarten now. So 120 squared and 4.34 divide. That's going to give me 3317.97 watts. So significant figures. Hey, let's assume we're going with 2 here. So that should be 3.3 times 10 to the second power squared watts. What do they get for problem 8? Oops, times 10 to the third. Sorry, yep, third. 3 decimal places over. They got 3.2 or 3.4, sorry. So I'm not sure how they got to 3.4 because I'm way below going up that next one. But you see where we got, right? Yep, I know. Either the book's wrong or I'm wrong. We'll figure out which one's which. But since I'm a dad, I'm right all the time. So just deal with that. Let's see. Doing power following circuit. We just did that one. So number 9. Yes. Now we get to a more complicated circuit. And I'm going to get rid of the rest of this here. So give us a little more room to do our thing. I'm going to leave those derivations there just because I don't want to have to go through them again in case we need to. So we now have, okay, fine. I'll draw it like they do with the battery at the bottom. Make sure I have enough space here. So we've got our and then this comes up and splits into yes, I did it. So we've got 120 volts here. We've got a 211. That is 211. 211 ohm resistor here. We've got a 301 and a 201. 301, 201 ohm resistors here. And it says that the electrician has a 1, a 5, and a 10 amp fuse, which should be used to protect the circuit. So when we're looking at putting a fuse in here and trying to figure out what size we want it to be, we want to figure out how much current is going to flow here normally under a normal circumstance. And we need a fuse that's a little bit bigger than that, correct? Slightly larger than that. However, because if we put a fuse in here that was lower than this, it's going to blow every time you turn it on. If we put a fuse that's much larger than this, then it's possible that something bad could happen and melt wiring somewhere else before the fuse blows. So first of all, let's figure out what the current is going to be if we just kind of totally ignore the fuse here. Just what's the current? Well, we've got voltage. To figure the current, we got to figure out the resistance. So we need to figure out the effective resistance. But we've got parallel and series, so it's a complicated mess, right? Whenever, and I think I've said this many times this year, whenever you have a complicated problem in life, break it down into smaller problems that you know how to solve, and then put those solutions back together, and you might end up with a solution that works for you in life. So the first thing we're going to do is, well, we could do them in series, but we really can't because we don't know what this one is. So we got to do this one first. So we're going to figure out these are 2 resistors in parallel. what's the effective resistance of this one? So our effective here is going to equal, oops, 1 over, now let me redraw that so it's easier to see on the video later. 1 over R effective is going to equal 1 over 201 ohms plus 1 over 301 ohms. That's going to be equal to, calculator work, 201, 1 over 301, 1 over plus, and then 1 over, oh, that's going to be 0.0083. So R effective, this one, is going to equal 1 over that, which I've got 120.5199, so 120. So this whole thing right here could be replaced so that we have a circuit now that would look like, let's see if I can draw it kind of smaller here. We'd have a circuit, a resistor here, effective resistor here, and then we'd have the fuse. So now we've got a problem where this is 120 ohms and this is 211 ohms with 120 volts, right? So this is the same as this, same problem. Different, like, you know, real world situation, but same problem. So now we add, to get the effective resistance here, we just add them together. So that's going to be 331. So we also have now a circuit. Let's do, there's our fuse. Here's our one single resistor, which is going to equal to equivalently or effectively equal to 331 ohms with 120 volts. Great. Now that's a much easier thing to plug into here. Now we can say that current equals V over R, which is 120 volts over 331 ohms, which is going to be about a third. I really don't even have to do the math here, I think, because the amps that he has, or fuses that he has are 1, 5, and 10 amp. So we're probably looking at the 1 amp fuse. But for the grader's sake, please finish calculating this out because they're going to be looking for that. So I'm going to go 120, enter, 331, divide to get a current of 0.363 amps. Got it? Yeah, 3662, sure. 3625 is what I got, so I rounded up. So yes, so the 1 amp fuse is the one he'll want to use. Make sure everybody's getting all that. Nobody has any questions. Awesome. All righty. So the last problem, problem 10. This is either a really easy chapter or we're just getting really easy problems here. What do y'all think? Y'all having a good time with this particular chapter? Yes, your brains are just too large. What is the power drawn by this circuit? Oh, now we get a really fun one. Yuck, I hate drawing. Let's draw on top here first. And it's going to come down to another resistor. Come down a little further to the battery. Duke. Yeah, I did it a little too long. There we go, another resistor. Fine, I'll make it the way they like drawing it. There. All right. We have, let's write them all in, 120 volts. We have, gosh, I can't even see these. We have, is that a 31? 31. 721 ohms. What are these two over on the side? 15 and 11. So 15 ohms and 11 ohms. So yes, this is literally child's play. If you have snap circuits, you can do the same thing, but with math and algebra. So again, we've got kind of a nasty looking circuit. If I'd given this to you at the very beginning of this chapter and said, hey, go figure it out, it might have freaked you out a little bit. But since you've got the principle ingrained in you now, hopefully, of spending almost a year with me, of taking a big problem, breaking the smaller ones, then putting it together, and you know that adding the series thing is a lot easier. We're going to do that last. So we're going to take this and replace it with a single resistor, effective resistance. We're going to take this, replace it with a single effective resistance. And then we're going to take the three that are now in series and replace them with a single one, and then we'll figure out their actual problem that they asked us for. So let's start with the one on top. Where can I do this? I have no space left on my board. I am going to erase my equations and we'll have to figure them out again. What are they asking for? They're asking power drawn. So we're going to have voltage, we're going to have resistance. So we're going to keep this equation right here. We're going to get rid of the other ones. Although you will probably need to write the other ones before you get this, because this is not an equation in the book. This is not one they're going to have listed on the solution. I'm leaving it there because it's easier for me. So to figure this one out, we're going to have parallel. So it's that nasty 1 over equation. 1 over 27 ohms plus 1 over 21 ohms. And that's going to be 27, 1 over 21, 1 over plus. I'm getting 0.0847 for that, and then 1 over that to get the actual resistance. Never forget to do that last step because it'll really mess you up if you don't. I'm getting 11.8125, blah, blah, blah. We're keeping the two significant figures, so it really pains me to do, but I'm going to say that that's 12 ohms. All right. So what we're going to do is we're going to take this and we're going to replace it with a single effective resistor that's 12 ohms. We're going to do the same thing with this one. If I don't get shot first. 15 ohms and 1 over 11 ohms. That's going to be 15, 1 over plus. I'm getting 0.1576 there. I do 1 over that, and I'm going to get 6.3462. This is now the actual effective resistance. But again, we're going to keep it at 2, so we're going to say that's 6.3 ohms. So we're going to replace this one. With 6.3 ohms. Awesome. We now have a nice series circuit. I know you probably don't need me to do this, but I'm going to write the equation out anyway, just so that you remember. So that is going to be 31 ohms plus 12 ohms plus 6.3 ohms, which is going to equal 31 and 12 is 43, 49. I'm going to say 49 ohms. Did I do that right? 31, that's 43 plus 6, yes, are effective. And because we're keeping the two significant figures, that's what we end up with. So now we can replace all three of these with a single effective resistor that is 49 ohms. Right now our problem is getting simpler and simpler and simpler. Now we got a really simple problem, and we're going to have power is V squared over R, which is going to equal power V squared 120 volts squared over 49 ohms. And so we'll be 120 squared, 49 divide. I'm getting 293.8776, which is going to be 2 sig figs. So let's say 290. They're going to go for 300, aren't they? I'm just anticipating how badly they're going to mess this one up. No, they do. Cool. So yes, 2.9 times 10 to the second power watts. So they actually got it right. 2 sig figs, 2.9 times 10 to the square, 10 to the second. Beautiful. All right. That is all of the review questions and the practice problems. It's not even 1 o'clock. So we're getting good at this. Yes. Oh, the resistor cube. I could cover the resistor cube, but before I do the resistor cube, oops, there was a question earlier. Someone asked me earlier to do something that I think was going to be an easier one to do before I jump into that one. Scroll back up and see what that was. Now I can't see if someone actually does it. Okay, scroll it all the way up because it was way at the beginning. Is there a way to determine how to divide the current flow in parallel resistors? I'm gonna have to work through that one and remember that one. Current flow through parallel resistors. Well, let's look at it. So let's do a nice simple diagram here. And let's say we've got a 12-volt battery and we're going to hook up I'm just going to try to make some simple numbers here. Let's do a 4 ohm resistor and no. Let's do this. Let's do a 2 ohm resistor and a 4 ohm resistor. Okay. So first of all, let's figure out what is the current that's going to flow through this if there's an effective, through, these wires at least. So this is going to be the effective resistance. 1 over is going to be 1 over 2 ohms plus 1 over 4 ohms, which is going to be a half plus a quarter, which is going to be 0.75, which is 3/4. So reverse that. That's going to be 4/3. Actually, wait, sorry. That's going to be 3/4 with ohm on the bottom. So the actual effective resistance is going to be 4/3 of an ohm, which is going to equal 1.33, whatever, repeating ohms. All right. So now we know that. We can figure out that the current, so remember V equals IR, that means current through the circuit as a whole is going to be V over R, and I'm kind of winging this, so forgive me if I go rabbit trail here. That's the thing that makes me think it's not hammering. So I equals V over R, that's going to be 12 volts over 1.33 ohms, but that's really over 4/3, so divided by 4 times 3, is going to equal 3. That's going to be 9. That's not 9 amps. Really? I guess it is. Okay, so we're going to get 9 amps going through this overall, but that's going to divide, right? It's going to divide as it goes through. And so we need to figure out if we've got 9 amps going through there and 9 amps coming through here, it's going to split. And so let's call it I1 and I2. I1 plus I2 is going to equal 9 amps because that's just coulombs. Think of it like a garden hose. It's coulombs per second. It's how many electrons, how much charge is flowing per second through this hose. And if we split the hose, it's going to be the same number of, coulombs going through. It's just going to be divided into 2 paths, and those are going to be different paths. There's going to be a different current down each one. But if I remember correctly, but the voltage difference, that's right. The voltage difference is the same here, if I remember correctly. Somebody joining. Rex is back in. Somebody dropped. And I believe this was even. Nope, it wasn't. Now you're here twice. Okay. Let me see if I remember this correctly. Because I believe that we end up with the potential difference is the same on each of these. Let me see if this works out. So if we have a potential difference of 12 volts here and here and 12 volts here and here, then if we had, let's see, where is it? Current is V over R. So if we ignore that and we just had the 2 amp resistor, we would have 12 over 2. So we'd have 6 amps. If we probably have 6 amps going through here. Let me double check. I think this is right. And then we have 12 over, yes, correct. So 12 over 4, right? V over R, 12 over 4 is going to equal 3. So we have 3 amps going down this branch. So when it breaks, 3 amps goes that way and 6 amps goes that way. And so the 9 amp splits, comes back together like that. Did everyone kind of follow what I did, or was that a little too quick on it? Kinda. Okay. So my first thing I did was I found out the effective resistance here. So I could find out how much current's coming out of the battery, basically. And that was kind of just thing like the problems we've done before, turn that into an effective resistance of 1.33. The current then for the overall circuit is going to be 9 amps. So then we got to figure out the current down each branch. Well, the current down each branch, we're going to have from this point to this point, we're still going to have 12 volts of difference. From this point to this point, we're going to have 12 volts. So there's 12 volts from here to here. There's 12 volts from here to here. So if we have 12 volts going across a 2 ohm resistor, 12 volts, 2 ohm resistor, we're going to have a current of 12 divided by 2, or 6 amps coming through this branch. We're also going to have 12 volts here, but it's going across a 4 ohm resistor. So 12 volts going across a 4 ohm resistor, you're going to have 12 over 4, 3 amps coming down this branch. And lo and behold, if we look at things, 6 amps plus 3 amps is equal to 9 amps. And so everything adds up, everything syncs together. As the 9 amp current comes out, if this was an effective resistor, because the battery doesn't know what all's down here, it's just pumping out charge on what's being, drawn. So 9 amps is coming out, but it gets here. How does it divide? Well, more is going to go through here than here. There's more resistance here, so less current can flow, right? Think of it like a river or something. It's a higher resistance, so less is going to want to go there. This is an easier path because it's only 2 ohms of resistance, less resistance. So more is going to come through here, and that makes sense. It also makes sense that this is half the resistance, therefore it's twice the current. So kind of trying to explain that through from different angles, how that works in reality, but that's how you would determine the current down each branch. All right, so let me see if I can, give me a second here. I'm gonna pull something up for myself. Close that window. So I haven't had anyone actually explain the resistor cube to me in any way, form, or fashion. So I'm going to assume that no one's going to do it. Let's see. What's going to be the best way? You know what? We have time. We do. We got another 30 minutes. So there are multiple ways to it's the best way to go about showing you the solution here. I don't think this one would necessarily would, but I'm actually double checking real quick so I can go through it much faster. Let's see. This one may be the best setup. Okay, well, let's do this. Let's give this a shot. See if I can make this work in 30 minutes or less. First, I'm going to draw the cube, and I'm not going to draw the resistors because that's too many squiggly lines. It would take me too much time. Y'all can understand that there's a resist. Each of those wires is a resistor, basically. Got all of them? Yes. We come in here, we go out here. So let's first of all, let's label the resistors. Let me see how they do this. A, B, I'm gonna try to keep it with theirs. So this one is A. Let's see. B, C. Okay. Whoops, my turn. Oh, I turned my cube that way. They turned it the other way. So this one is B. This one is C. This will make it easier when I draw the whole thing out. A, B, C, D. Well, I know I'm coming out of order, but it's easier to label in this way. K is this vertical. E is back over there. I think that's L. I'm gonna go lowercase l there. I and J. I is back here. J is up here. And H is here. And G is this vertical here. So we've got A, B, C, D, E, F, G, H, I, J, K, L. Okay. So each of these resistors are labeled like this, and I'm just going to use these letters throughout. So the next thing we need to do is let's flatten the cube. Okay. Instead of flattening the curve, we're going to flatten the cube. And so as the current comes in, it's going to branch into 3 branches, right? So let's see, is the easiest way to do this. I think this is probably going to be it. Come on. Scroll down here. Make sure I get the letters right as I go. All right. So we come into our point. Yeah, I'm going to need like lots of room. I'm going to start in the middle here. Come in. It's going to branch into 3 resistors. As it goes. A, B, and C. Okay, so we'll just label those. I think they go top to bottom. They do go top to bottom. Good. A, B, C. Then, so all of these points are essentially going to be equal because it's an equal split. This is a very symmetrical cube. And that's the key here is everything is symmetrical. So every branch is going to look the same. Now, when if we go follow the A branch, I think that's where we go next, yes. Then that current could go down either D, E, yes, D or E, right? So this one could go down D or E. So we're gonna do, and I'm gonna draw this a little bit separate here just to give an example. Actually, let me just do this. E, F, these are horrible resistors. Bear with me for the sake of speed. G, H, I, 2, 2, 2. Okay. So A can branch and go down D or E. B can branch and go down F or G. C, D D, E, F, G. C can branch and go down H or I, okay? So, but the thing to look at here is things can cross across too. So things are going to be kind of backtracking other ways. Give me a chance. Actually, I want to try to see if I can explain why these are like this in just a minute. Let me go back to the other end though. Coming back together though, the other branches of the current are going to be very much like when it was going in. We're going to have J, K, and L. And then out. Now here's the part. This actually doesn't really matter. Connects in like that. So that is the same circuit drawn out in flat form. I'm getting a question mark here, yes. So let's follow the current as we go. We essentially have current coming in here and then going down this plane, okay? Going DEKL, right? We've got current coming here and it's going FGJK, right? And we've got current coming here. Actually, wait, sorry. It's going, I think B may be the easiest one to follow. This one right here, B, is going FJ and JK. Or sorry, FG, JK, and out. It's going, splitting, coming back together, and out, the end. Does that make sense right here? Yeah, absolutely. Jump in the mic if someone wants something.
Well, my question is you put so essentially what you're going to do is you're going to have 3 different series or parallel circuits. And my question is, wouldn't be you have the first parallel and then each parallel breaks into to another parallel? And then they go back into another one? Or does that work out the same?
There is another way you can do it. And is that the one where you found that the equations got a little more complicated?
No, I made that one up.
Oh, okay.
I didn't look up anything.
Oh, okay. So yes, you can look at it going here and branching and branching. So having essentially a parallel with 2 series resistors on each branch. So you could say you have, you're coming in with A and you're branching, let's do it this way, with, I'm just going to do straight lines. We all know these have resistors on them. So A comes in and goes to DK branch and EL branch, right? And then out. So squiggle in, squiggle out. Wires going out. So let me put the A a little better. A. So this is what you're talking about, right?
I don't think so. I was doing what I think Demi's trying to point out in the chat is that A goes to D and E, and then B goes to, or I'm not sure. I didn't write my cube the same way you did, but
yeah, I understand. Okay, so yeah, so let's we can work that way. Let's try to see what we can do. So A comes in, branches to D and E. B comes in, branches to F and G. I'm going to run out of room. And then C comes in and branches to I and H, right? Well, let's keep them in order. H and I. Are we kind of on the same thing to start with? Okay, cool, Demi. Yes.
Yes, sir.
Okay, so then D goes to K, right? And out. D goes to K to go out. E goes to L, joins back up, goes out. F goes to K. G goes to J, and goes out. H goes to J, and I goes to L. Did I get all those right? Holy moly. Yeah, so the problem here is that we've got multiples in each of these and they overlap. And so we've got extra stuff going on there. There is a way to work it this way. You just got to take some extra care into some things. So this diagram actually takes this last half into account, essentially, in that we are bringing them back together into this parallel circuit in series with the rest. Click on that link and see what that looks like, because that may be it. Yeah, you could draw it that way too. And then you have to break it all up into what's series and what's parallel, right? So let's see what we end up with though first here. So let's figure out these three equivalents, okay? I think I said these were all 1 ohm. Is that right? Resistors, which is gonna make this math like super duper easy. So 1 over 1 plus 1 over 1 plus 1 over 1 equals 3. And so this becomes a 1/3 equivalent resistance. 1, 2, 3, 4, 5, 6. This becomes a 1/6 equivalent resistance. 1, 2, 3. This is another 1/3 equivalent resistance. 2/3 plus 1/6 is what? 2/3 is 4/6, 5/6 of an ohm. Now, the question is, do the other ways get a similar answer? 5/6 should be about 0.833 repeating, I think. If you actually did math on a calculator. Yep. There you go. So there are obviously multiple ways to do this. They're different paths. There are different ways to break these down. That's why grading physics tests is so hard, because there are multiple ways to look at a problem and to break it in simpler ones. You can look at it this way, how they break down. You can look at it this way and then deal with, you know, some extra things there. Let's actually take this just as it is and see what we end up with. So these would be 3 circuits in parallel. Correct? So let's find equivalent resistance for these 3 setups. So this is going to be 1 and 1. That's going to be 2 over here, 2 over here in parallel. So that's 1/2 plus 1/2, which is going to make that 1. And then 1 over that is going to be 1. So all that's going to be 1 plus 1. So that's going to be 2 ohms. This would be 2 ohms. This would be 2 ohms. Which means, and these are all in parallel, so that would be, so I don't think this quite works. That would be 1/2 plus 1/2 plus 1/2, so that'd be 3/2, which flipped would give us 2/3 of an ohm, which is not quite right, but because we've got these that are being taken into account multiple times. Let's see. Trying to think other ways to look at all of this. Let's see. The reason why this works here is you want, if you find place, so if we apply a potential difference here, where are the places? Yeah, I might be breaking people's brains. It's okay. This is way beyond what's required in the book. This is kind of the extra stretch thing. So we're good. Let's try this. Let's back all the way back up and say, how did we get here? Okay. How did you come up with this? Think of where the potential differences are the same. Kind of like when we were splitting the current, like we split the current before, you know, with that 2 and the 4 ohm and the 12 volt battery. It was 9 amps and it split to 6 amps and 3 amps. And we said the potential difference between these 2 points is the same as the potential difference between these 2 points, right? Because it's here. So where are the points on here that we're going to have the same potential difference? And so as it splits here, whatever this voltage is, it's going to go across 3 equivalent paths, right? And this is symmetrical. So path and face, path and face, path and face. Whatever it is, we're going to have a completely direct equal 3-way split here. And so that means when we get to that point, and that point, we're going to have an equivalent. I mean, it's not going to be the same as here. We're going to have a voltage drop across the resistors, but the voltage between this and here is going to be the same as from here to here and from here to here. Okay? Across this face, and across this face, the potential difference is going to be the same. And so we could just like throw away that part of the problem and just have these 3 cube faces. And then we can look at this and say, oh, that is the same as branching all the ways like this. Okay? Add it up. You can kind of break them in parallel. So it's that in parallel, in parallel, and in parallel. And then they come back. But we've also got, let me see, I'm going to do X's here. We will also have, going from the reverse direction, because you can kind of flow things forward or backwards here, coming up here, coming up here, coming up here, we're going to have equal currents coming in these 3 branches, right? Like this, yes. And so the same thing occurs here. That's how we get this equivalent resistor at the end on the K, the L, and the J branches. And so what we've got is we've got the D, the E, the F, the G, and the H and the I are all in parallel here. So we've got these 3 points and these 3 points, yes, that way, are equivalent voltages. They everything comes to the same point, essentially. And so we split here, we come together here. What we have in the middle is D, E, F, G, H, I, all in parallel. Does that help visualize? I know I probably won't get everyone, but those that had a problem with it, try to wrap your head around on that. And so some of it is kind of that spatial reasoning, where they take the cube and they unfold the cube and they say, or they have the unfolded shape on the SAT and you go, oh, what shape will this be when it's folded up? And you have to kind of visualize some of that. Some of it is recognizing, knowing the physics of the where things are, the voltage will be even, so you can make it a simpler problem. And some of it is just seeing the symmetries that you have. One thing physicists really like to see, the word symmetry is used a lot in physics, because if you can look at something one way and the other and it looks the same, like in this case, we have a line and a face and a line and a face, face and a line and a face on the cube, then we can break things into simpler problems because of the symmetries that are involved there. So I know y'all, most of y'all probably aren't going on to like careers in physics or whatever, but do at least take some of that type of problem solving mechanic, out of this class, and you'll hopefully do some well with it for you. There was another question. So I did the cube. Okay, I did the cube. Were those all the questions? It is 1:20 right now. We could theoretically end early unless anyone has any other questions. Test on this one hopefully will be just as easy for you guys. I can be available tomorrow night. I will put myself available. None of your parents joined this last Tuesday, so I don't know if people are finding it easy enough to grade for themselves. If they have any questions, definitely text me. I will jump on from like 7 to 7:15. If no one's there, I will, drop off tomorrow night. But if any of your parents have any questions, have them text me, call me, email me, whatever is fine, and we'll take them from there. We got one more module left on magnetism, I believe. So everyone have a great week, and we'll see you on Thursday in a few days.